No, I got two here. Mm. How's it going now, Ron?
Not too bad, Professor. How you doing?
Did you not take the test today because you were happy with your previous grade?
Yes, I'm okay with it right now, and I also did have some other stuff that I had to take care of. Yes,
Okay.
sir.
No problem. Just making sure something didn't happen where you had to miss it or something.
Oh no, I do appreciate the way you set it up. Thank you.
No problem. I'll make a copy available for you. I think, one other student that didn't take it for that reason. So I'll make a copy of it available for you so you can use it to practice by.
Oh, for the final, right?
Uh-huh. Yeah.
Did you get a tornado warning over there?
Yeah, they got one for our area as well. I think ours is out is in the clear now, but I know at least southern Virginia Beach, north southern, or excuse me, southeastern Virginia Beach area and Virginia area is still under it.
I
Actually,
see.
no, they might be finished now because I think it stopped at like 5:15.
Oh, it was pretty bad over
Was it?
here.
Did you get to see a tornado?
I hope I didn't.
Just looking at the test results now, the average was about the same.
Oh, okay. Oh, you know what? While nobody's here, I was wondering if I could ask you, like, the syllabus right now is.
No, no. In fact, I noticed some of the test stuff were put in the wrong category. So I should have all that worked out by Monday. I'm hoping to have it by Friday, but I got to work through the grade book and get that fixed. But then the grades should be accurate. The only inaccuracy that I'll have in the grade book after that day, which, like I said, I hope it's Friday, but it definitely will be by Monday. The only inaccuracy then will be that I'm not dropping any of the test grades or any of the homework grades until the end of the semester. So it keeps your grade a little bit lower, but it keeps students from getting a little too cocky and making a boo-boo at the end of the semester. I know they're adults and I'm supposed to let them make them, but I still feel like I don't want them to.
Uh,
It'll be accurate then, though.
Sorry, what you said right now, what isn't accurate, the lowest.
It is not accurate. I mean, if you took the individual grades and did the calculation yourself, that would come out accurate. But what's not accurate is I've noticed some of the tests went into the wrong categories. Like all the face-to-face tests are supposed to be in one category, and then the online tests are another. But it didn't do that. Some of them are in the wrong spot, and I got to go through one by one. The reason why I haven't done it yet is there's actually, from where I copied old courses, there's old versions of the exact same names. So I've got to track down exactly which one's the real one so that I don't accidentally throw away the one that everybody did and I lose the grades. So until I get all that straightened out, I can't really do anything. That's why I'm hoping to get it done. Like I said, this week by Friday or Monday at the latest. Hello, Gabriel.
Hi,
Mhm. How are you doing?
I'm all right. How are you?
Not too bad. Just sitting here looking at the tests and all that good stuff. So I was just telling them it looks like the average turned out to be about the same as it was last time. It's a little higher. The average last time I think was 61, and this time it's 63. But the highest grade and the lowest grade is higher for this one. That's a little better. Uh, it would probably be better, but I also got two students that normally make good grades. They didn't take it just because I'd give them the option of uh basically me taking just the higher of the two grades. So two or three people didn't take it. But we'll work on it. I'll get whatever your grade is, don't worry. It's not a if you didn't do well, it's not a deal breaker. If you did well, it could help you a lot. And I'm saying that out of ignorance because I clearly all I was doing was looking at the numbers and I tried not to look at anybody's names.
Professor, I have a question.
Go for it, Nora.
Um, is it relevant is it more relevant to ask about practice tests, like if we missed a practice test or not at the end of class, or like at the end of the semester than now?
No, you can
Because
ask
I'm
it now. Yeah. Did you miss
okay.
some of the practice
I
tests?
Yeah, so I guess I had lost track in the practice tests to 17, 18, 19, and 20.
Uh-huh.
I wasn't able to complete that one. And then there was one that ended today, like it closed today.
Okay, that's not supposed to close. In fact, let me change it right now. That was supposed to be, oh, oh yeah, that one closed today, but that one's not required because that was the errant one that included chapter 25. So that's not going to count against you.
Oh, okay. All right, I'll just make a note of that.
Yeah.
But that other one, should I just send you like a text or an email about it so I can finish it?
Yeah, 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 send me a text about it. I'm going to change this practice test 6 real quick and make sure it's not in the wrong category. Oh, good.
Gotcha.
It's in the wrong category, which means it's the right thing.
All
Uh,
right, gotcha.
so yeah, that one's not counting as a practice test, and therefore it won't count towards extra credit. I'm not sure if I can do anything about the second one. I think about it a little bit. That's why I said send me a text.
Okay, thank you.
No problem. Uh, it looks like okay, it's time. So, and we've got 5 of the 8 people or whatever in class. So I was just saying, Nora, telling everybody that I did, and welcome Zhang and so on to, I was just telling everybody that I looked at the grades and it looks like the class average was about 2 points higher than it was the last one, the last face-to-face one. That one had an average of like 61. This one has an average of like 63. However, the highest score is higher on this test at 93, and the highest, or excuse me, the lowest grade is also higher on this test, and like I think the lowest was like a 39, whereas last time the lowest was like a 24. So that's an improvement, and the standard deviation is roughly the same. But in this case, we had 2 or 3 people didn't take this test at all, and they're ones that knew their grade was pretty good from the last test, so they chose not to take it, and that actually will make their would have made the average even higher. So I'm feeling pretty good about what everybody did, even though I know some people are outliers and didn't get that great of a grade. I am still going to take the last, which I think was called test 2. I'll take the highest between that one and this one, which are the 2 face-to-face tests we've had so far. And that's the score you're going to get for both of them. And I sort of misrepresented that last time because I think I was suggesting that since I'm taking 1 grade and replacing it for both tests, that would make it as if there's only been 1 test. No, I'm keeping it as if there's already been 2 tests. So each of those only count as 15% instead of the 22 and a half that I thought it was going to be. So I did forget that. I was also telling Elron, the grade book right now is not that accurate. I discovered there's a lot of issues regarding the categories that some of the tests and practice tests are in, as well as some of the homework. So I got to go through and do all that. Normally I do this very early on, but in this case, when I copied stuff, somehow I've got multiple copies of assignments with the same names. So I've got to go through and see which ones students actually did. And occasionally there's an issue where a student did one that no one else did, but everybody else did the other one, in which case I got to give that student credit. So I'm going to try to work for that. But I should have that cleaned up. I'm hoping by Friday, but I might even have it cleaned up by Monday. It's just I got to do a little bit of testing to make sure I don't accidentally erase one that has students' grades in it until I've recorded the students' grades. So that'll be right. I have been, oddly enough, people were talking about how bad Canvas is. It can be really bad. I've actually got a good quote unquote mastery of it, where I feel confident about it, and I still do a backup calculation. I usually will do one by Excel. I do one by hand first. I just take a student at random, check it by hand, and then I do an Excel and I compare that to the hand calculation. And if that's wrong, then obviously I see which one's wrong, and then I compare that to the Canvas calculation, and they're normally right at the same. So, but I do that either way. So that's just another layer of obsessive compulsive that I do to make sure everybody's grades are right. Anybody have any questions before we get started?
2 questions. Sorry,
Yes.
you rephrase what you said earlier about like the two tests being 15% or 22.5?
Yeah, so it was supposed to be test two, this test, and the final are all the face-to-face tests. And generally, by me putting it over three, it used to be just over two. And I made that 45% of the grade because that's literally the only test I know exactly who's taking it and all that stuff. So now it's over 45, but over three assignments. So I'm not erasing one of the tests. I'm just taking test one and test two, or excuse me, the last test, which was test two, and today's test. I'm taking the higher grade of those two and filling in for both. So that now means you have three test grades. Two of them are identical, and the third one it will be the final exam, and each of them counts 15%.
Oh, okay.
Does that make sense?
The next question, I know you said like the grading balance and the syllabus isn't accurate right now. Do you have an accurate number for each?
Yeah, so right now, like I said, it's got various grades are in the wrong category, and the category is what it grades by, and then it also takes not only categories, it erases a certain number based on what I said in my syllabus. So all that stuff's not homed in, and I won't put in the drop grades until literally like the day of the final or something. That's usually when I do that, specifically because I don't want students to get a little too cocky and accidentally screw up a final because they thought they were better off than they were. So that part's never going to change until literally probably the morning of or the night before the final. And I do that on purpose. Did I answer your question? Because you were trailing in and out when I was trying to hear you.
Oh, sorry, I must have like worded it bad. I meant as in like, so the in-person test, 45%. What about the other percentages?
Let me pull that up on my syllabus real quick just to check. In the modules, I'm looking at helpful documents and links, and I'm looking at the summer 2023 test. Someone just tried to come in, so let me let Bohan in. All right, so looking at the document, double check what's going on here. I'm scrolling down to the grade section, and I have that the online tests are worth 10%. And I did have where the comprehensive final was worth 25% and the comprehensive midterm was worth 20%. But what I did, I announced to you guys, even though I didn't change it in writing for whatever reason, but what was listed as the comprehensive midterm and the comprehensive final, I made to just face-to-face tests, and that's all going to count as 45%. So the online test is only worth 10%.
Online test, 10%.
Mm-hmm. And I do drop the lowest of that one. I drop the two lowest homework activities. I don't drop any conceptual homeworks. And lab grade counts 20% as well. And the practice test is just 5% bonus.
Okay.
Okay.
Professor Younger, sorry, I just got here. So you said the finals like 25. I saw you said that last time you said final was 15%.
Yeah, I explained that earlier before you got here. So what happened was this syllabus is the version I had originally, but then I realized I had 3 or 4 days that I could give you a test face-to-face. So instead of taking that 25% and putting it on the final and 20% being on the midterm, I decided to spread it over 3 tests. It doesn't say it in the syllabus. And in fact, if someone does so well on the final, that would help them, then I'm going to go back to that 25%, at least for that one specific student. And that's what I have to do because that's what the syllabus says.
So, but if we,
it should be 15.
Okay, just in case, like if I'm not doing very well on final, the final only count 15% of total.
Exactly.
Okay, thank you.
No problem. Yeah, since I didn't put that in writing before the drop date, then I still have to check that version of the calculation, and if someone looks like they're higher using that version, then I have to give them that test, that version of the grade. Anybody else? All right, well, I talked a little bit about 25. I'm going to go ahead and do a lightning round of chapter 25 now. And I say lightning round because I went ahead and took the time and wrote the questions out a priori. And then I'm just going to go through and solve them. And I'm going to do a little less of the talking, but I did mention, did I tell you guys about how I make batteries for like the hands-on science museum that I used to work with in Elizabeth City? Did I tell you all that? Okay. I didn't think I did. So in the opening part of of chapter 25, they talk about how the battery was invented, and it's really a good thing. But basically, one person was working with dead frogs, and he kept noticing that under certain circumstances, the dead frogs would still kick and jump and stuff like that. And some people thought it was, the life force or like a soul type thing. But then he later discovered that when he just, completely cut apart the individual frog to where it was just like a leg or something like that, he could get the individual muscles to do the same thing. So that was less convincing of it being part of the soul. And in fact, he had a sense of what it was. Volta comes along and decides to try to make a pile, and that name is so familiar that we still use it today. Well, we sort of do with power, for instance, in nuclear power plants, like Enrico Fermi, when he first made a nuclear reactor that was sustainable and controllable, basically. When we made that, he called that a pile. And the reason why is basically, if you want to make a battery, one thing you could do is imagine taking a little prescription bottle, mainly because it's cylindrically shaped and I could fit like washers in there and a liquid and it would fit nice and neat. What I would do is probably take, let's say an aluminum washer, and maybe I'd solder a wire to the first one, and then I'd put the soldered wire side down in the bottom of the prescription bottle. And then I personally, you don't have to do it, but there's reasons for it that in my experience, it tends to work a little better. I'd put like some kind of gauze, cotton or something like that on top of it. And then after that, I would put a penny, because the penny is covered in copper, or you can put zinc, a zinc washer, which is the shiny, that bluish chrome looking stuff that you see in Home Depot and Lowe's on washers and screws that are claimed to be outside. That's zinc. It's crap. It's really horrible metal. But anyways, you put that on top of there, and you could, in principle, solder a wire to the top of that, and you could take and connect your black probe, your COM from your multimeter to one of the wires, and your red, which is the V omega port of your multimeter, to the other one, and it will read positive if you do it the right polarity, and that's about the electronegativity of the individual elements used. But once you got that right, it might read like 0.2 volts. So that is a battery source, provided we had some kind of electrolyte solution in there with those two dissimilar metals. So electrolyte solution, pretty much water that's not distilled will work. Alkaline solution would work really well. That's why they call them alkaline batteries, but also a acidic solution would work as well. So you could put vinegar in there, which is acidic. You could put some kind of soapy water if you wanted, which that's more basic or caustic. Actually, yeah, it is basic. Or you can put lemon juice or sugar, or water, or something like that. But pretty much anything that has some free ions floating around is going to be an electrolytic solution. Now, here's the neat part. Let's desolder that top one off of that penny or the zinc washer. Put another piece of gauze. Put another piece of zinc. Put another piece of gauze. Put another penny or pieces. In this case, the first case is supposed to be aluminum. Now, this case is supposed to be zinc. And then another piece of gauze, then aluminum, then another piece of gauze, then zinc, then another piece of gauze, then aluminum, then another piece of gauze, and then zinc. Now we've got like 3 times as much. And in fact, instead of it being 0.2 volts, now it'll be more like 0.6 volts. Yes, I dropped 2 lowest homework grades, Nora. Anyways, that piling up of different metals is an obvious reason for them naming it pile. And that's also why we came up with the symbol that we use for battery, which is in most cases usually just one short line and then one long line. But you will see a lot of text still have long line, short line, long line, short line, or sometimes they'll even have 3 pairs like that. And that's really, reminiscent of the different metals being stacked up. Your book actually has the schematic drawn by Volta, where it actually shows Z and A on everything, which I think, if I remember correctly, was aluminum and zinc that they happened to be using. But anyways, the more you stack it up, the higher the voltage could be. You could also make it. I made them at Port Discover, which is a hands-on science museum. I was a part of the original committee that created it. And I would go there and show kids how to make batteries and various other things, teach them about astronomy. But the way I would teach them is I could bring in a lemon or an orange or an apple. You can even do it with a potato, just about anything. And what I'd do is I'd take a big piece of copper wire, like some number 10 wire, and just jab it in one end of the lemon or the apple or the tomato or whatever, and then take a galvanized nail, which is essentially covered in zinc, and jab that in the other side. And you could measure the voltage across that, and that would read on the order of 0.3, 0.4 volts. In fact, I could connect them in series like that, where it goes nail, wire, nail, wire, nail, wire, nail, wire. And each one of them would contribute an additional 0.3 or 0.4 volts roughly until you could get it pretty high. Now, I usually didn't get enough of them to actually turn on an incandescent light bulb. I mean, you could get current going through it, but you just couldn't get it enough current to make the light bright, which you all saw when you did your lab in lab, of course. But you could definitely turn on an LED, which just normally has a turn on voltage of like 0.6 volts, and then it'll automatically come on. So you can do stuff like that. But once you have the capacity to make a battery, then you can actually study things other than just phenomena of individual charges jumping from one thing to the other. You can actually sustain a flow of charges, which is what a current is. A current is dq dt, which is the instantaneous rate of change of charge. And what I mean by that is you can sort of imagine a little gremlin sitting on the edge of a wire, and he's drawn this imaginary plane perpendicular to the wire, and he's just sort of counting the charges go by 1, 2, 3, 4, 5, 6, 7, and then he reports that number every second. Boom, 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 real fast, right? Now those charge carriers happen to be electrons, so if you take the total number of charges that flew by in 1 second, then you take that and multiply it by 1.602 times 10 to the negative 19th, which is the charge per electron, and that'll give you the actual current in coulombs per second. Now, the electrons are going this way, but what we've defined as current is conventional current, and that's actually going that way. So he would say, yeah, see all these electrons going this way? He said, yeah, that's because the current's going that way. Okay, so that's the only downside of that, is we've got that backwards thing. But there's really only one experiment that you can do that we've done that actually shows exactly whether that's positive or negative particles carrying it, and that's called the Hall effect. Basically, the Hall effect would be, you imagine this wire, say, going across here, and if you run that wire with current going this way, say, if you put a magnetic field pointing that way, if it's positive charges, then QV is a positive charge times the velocity, which is this way. And then cross it with B, which points into the screen for me. That means the positive charges are going to go downward, according to my right-hand rule. That's something we'll learn a little later. So you'd expect the bottom side to get all these positive charges. And then, of course, that would force the bottom of the wire to have a higher voltage than the top of the wire. Now, if, on the other hand, this current going this way was a result of negative charges going this way, then QV is still that way, because Q is negative now. So QV is that way, and QV plus B is this way. So again, you get negative charges down at the bottom, and that would make the bottom the lower voltage and the top the higher voltage. Turns out that's what happens. We actually get the bottom of the wire would be lower voltage and the top of the wire would be higher voltage. So we can tell specifically that that is due to negative charge carriers. So unless you're, measuring the voltage from one side of literally side of a wire where current's going perpendicular to it to the other side, you're not going to know the difference between positive charges going one way and negative charges going the other. Okay. Any questions on that? I really highly recommend you trying to read these chapters in the electricity and magnetism part, because one, there's a lot of applications, there's a lot of terminology, for 2. And then for 3, really, you get a whole backstory that makes sense and helps you better understand the world more than I can tell you by just talking to you each day. So let's go ahead now that we've covered that issue, and let's look at, for instance, chapter 25. And we'll start off with chapter 25. It's actually called Electric Current and Resistance. And we're opening up with electric current and resistance and the electric battery. I've already described that. Then electric cells and batteries, they talk about that, as well as electric cars. Then they go on to electric current being dq/dt, or the number of charges or the amount of charge passing a particular place in time divided by time. So we're done through all that. What I want to do now is just open up with this first example, which I'm calling example 1, and I'm going to share my screen with you. And you'll see the equations that I use, some of which you already know, basically because in one case it's identical to an equation you used before, only that equation was for the length of a piece of metal or something, whereas this equation is for the resistance or the resistivity. So other than that, it's essentially the same equation. We also have some common sense equation that I'm going to derive, at least heuristically, with talking to you via sentence. So look at this problem right here. It says a current of 16.0 milliamps. So I'm already introducing the idea of current being measured in amps. So, and I've hinted at that before. That's why I didn't feel too bad about it. But just for the record, in case you're needing to realize it, I is equal to dq dt. And of course, that means the units of I are coulombs per second, which is defined to be the ampere. Okay, so that's a capital A. Now, it turns out an amp's a buttload of current. It's a really lot of current, okay? It takes about a milliamp. A single milliamp can kill you if properly applied. So it's more often that we run into milliamps and microamps and stuff like that. But if you're dealing with really big machinery, or if you're dealing with, for instance, starting a car, yeah, you're going to deal with whole amps. A typical, even a small car like a Honda Volt or something like that, well, a hybrid car would start with on the order of 30 or 40 amps, whereas like a Mack truck might start with a couple hundred amps, and a regular truck might start with 90 to 100 amps. So just to keep that in mind. So this is a current of 16 milliamps, flows for 300 or for 3.00 minutes. And make sure y'all see that decimal, because I clearly didn't. A, how many coulombs of charge will have passed through the wire? And B, the current is actually made up of electrons flowing the opposite direction of conventional current. How many electrons travel through the wire? So we'll start off with part A. Part A, we use, at least on an average basis, I is really dq dt, but I is approximately equal to delta Q over delta T. So if you want to look for the number of coulombs, you just say delta Q is equal to I times delta T. And I, in this case, is 16.0 times 10 to the negative third amps. And delta T, 1 minute is 60 seconds. So 3 minutes should be 180 seconds. And I'll put a decimal there so we realize it's actually 3 sig figs. And now you see, since I told you the amp is a coulomb second, when I multiply the amp times a second, I just get coulombs. So let's go ahead and compute what that is. That's going to be 16 exponent negative 3 times 180. And that gives me 2.88 coulombs. Now you might remember, hopefully you do, that I told you a coulomb's a big unit of charge too. So that's important to know. So yeah, we're still looking at coulombs of charge going by, even with 16 milliamps. Okay. Give you some perspective. I bought from Wish. One of the wonderful successes I got by buying from Wish was a little device that measures and lets me know the voltage and amperage going through my phone charger as it charges my phone. And what I discovered is my phone charger charges my iPhone with on the order of 100 milliamps. So that's something that's kind of interesting as well. They run basically on 5 volts. All right, now that we've got that, let's do part B. The current is actually made up of electrons flowing in the opposite direction. So if the current was going to the right, that means electrons are flowing to the left. And what we're asked in part B is how many electrons. So the number of electrons is equal to the coulombs, which would be delta Q, over the Q per electron. So that's the way we'd write that. So if I put the 2.880 coulombs and I divide that by this number, which hopefully you'll have memorized, 1.602 times 10 to the negative 19th coulombs per electron. Now, by writing it coulombs per electron, that forces the unit up top to become electrons, which is nice. It makes me make sure I did the right math. So if I would have multiplied this by 1.602, it would have came up with some quantity per electron, and that doesn't make any sense. So that's a nice helper for me. So I'm going to take that 2.88 and I'm going to divide it by 1.602 e to the negative 19th. And that gives me 1.798. That's 1 extra sig fig times 10 to the 19th. E minuses. So remember 10 to the 23rd is roughly a mole. So this is what, 1/10,000th of a mole? So yeah, that's a buttload of electrons. A mole is a huge number. Remember, a mole is about a factor of 10 to 100 larger than the number of stars in the visible universe. So that's a pretty big number. Okay, I got 10 to the 22 when I calculated roughly the number of stars in the visible universe. I got 10 to the 22 power. So 10 to the 23 power is 10 times more. Any questions on that? All right, so that's the first problem, and I think that's a pretty straightforward one. It's supposed to be a chucker problem that should be relatively easy. Hopefully it was that way for you. Let me look and see if there's anything else I want to look up. Are y'all having problems with your Pearson app or your ebook? Like it's buggy or anything? Okay, like I'm reading section 25-4 and I flip to the right and it just jumps to like chapter 6 or something at random times, but it'll still say chapter 25. You have had that happen, Nora?
Yeah, this morning when I was trying to use the textbook to review, I couldn't stay on one page no matter how hard I tried. Like as I was scrolling down, it would flip to a different page. So I would like have to use Control F and search in the textbook and then like stay on like one block.
Yeah, that's aggravating. I'm going to let them know. I have contacts with the direct people because I used to work for them, so I'll let them know about that. It's not looking good for the 5th edition. If you look at section 25.1.1, they talk about electric cells and batteries, and what they have drawn on there. This is figure 25.3. If you want to look it up, I will just write it right here. 25-3. They basically have like a beaker full of sulfuric acid, which you all know, of course, is H2SO4. And no, I don't think you really know that. I'm just being funny. So maybe you do. If you're taking chemistry, you might remember. So it's got sulfuric acid in there. And in the sulfuric acid is basically a carbon electrode and that's in fact counting as the cathode. It's plus. And then the zinc is another one, whereas a typical battery that we're running into nowadays is lithium ion. In that case, the lithium acts as the cathode and the carbon acts as the anode. But in this case, it's zinc. And this is, in fact, another way to make a battery. Okay. It's also a way, by the way, of plating metal. So if you have, for instance, a necklace made out of some, crappy steel or something, but you want it to look nice by, giving it a coat of gold or silver, you basically find a chemical, or hopefully the steel will do it, but basically you can find that it's more likely to hold on to its electrons than the gold is. And then you can set up the voltage in such a way that the little atoms of gold will fall off of the atom or of the gold rod that's sticking in it and will drift over and stick to the steel. So that's how you go about gold plating. Hopefully they taught you that in chemistry, but that's again another way of looking at a battery as opposed to just taking about fruits or dissimilar metals in a bottle or something like that. Your book also takes time to show you some typical conceptual ideas about how you go about connecting a battery. So remember, when you're going to make a power source, you actually have to not only run a wire from the positive side of the power source, which in DC world is often a battery. So you take from the positive side, you run it into something, say maybe you touch it on the threads of the incandescent light bulb, and then it runs in through the threads, goes in the wire, and then the wire is made of tungsten. It's got those little curls in it. And if you get a high enough current, it gets so hot that it glows. That's the incandescent light bulb. But that current's got to not only leave the light bulb, it's also got to re-enter the battery. So it then comes out through the very bottom of the light bulb, where you'll notice that there's something shiny between the gold of the threads of the light bulb and the dullish gray looking center dot of the light bulb. That dullish gray is often lead, because you want to be able to just touch it with a soldering iron, and then the wire can be melted right into it, and you've got it soldered fresh to the other side. The shiny stuff around the dull metal is an insulator protecting it and insulating it from the threads. So the current can actually go up the wire filament and then come out the wire filament through the bottom of the light bulb, and then it can go back into the negative side of the battery. So you always have to have that complete loop when you're doing that. In this case, just for the record, this would be one of the many ways you could draw the battery. You can draw it with this, where this side is the plus side, this side's the negative side, and then you run over here. And what I'm saying is, for the incandescent light bulb, you'd have the thread part, which is like this. And this would actually touch there. And then this would go up and come down and come right here through the middle. And then this little part will do this and come back here. Okay. So your book does take the time to do some conceptual ideas of how to connect batteries and stuff like that. For the record, your AA batteries, your AAA batteries, your C batteries, your D batteries, they're all a voltage of 1.5 volts. Now, when you first buy them, they'll read 1.72, maybe down to 1.58, something like that. And that's because once you draw current off of them, they're going to drop down, and the manufacturer wants them to stay at 1.5 for a long time, because that's the lifespan of them. They hope the lifespan's a long time, not too long, because they want to sell them to you again, but they want it to some extent for some time. So as long as they're having a terminal voltage of 1.5 volts while they're while they're delivering current to the item, then they're considered a fresh battery. So that's why they have the 1.72 to 1.58 volts as a typical reading without it connected to anything. But those are all like that. And then, of course, the square batteries with the little grappling hook looking thing on one side and just a circle on the other. That's a 9-volt battery. And I definitely suggest you all put your tongue on one of those. In fact, find the one at the store that's still there and stick your tongue on that. No, you'll go to jail for that. And it's also a high probability that you're going to get some kind of illness or something. So anyways, but yeah, that is a fun old pastime, is to stick a 9-volt battery against your tongue to test it and see if it's going to actually sting you or not. All right, so that's the first example. Let's look at another example. It says a typical portable phone charger has an output of 32,000 milliamp hours. A, is that quantity energy like joules? Is it volts like volts? Is it, electric voltage or electric potential like voltage or volts? Or is it time or what? Anybody have any idea what that is? So you can ignore the milli, because that's just a times 10 to the negative third. But everybody remembers what the amp was, right? I just mentioned it to you right here. So what's the amp? So the amp's a coulomb second, right? And notice after that is a multiplication and then an H for hour. Hour can be made seconds. What happens when you multiply seconds times amps? When you multiply seconds times amps, the amp is a coulomb per second. Yeah, so you get coulombs. So in this case, we're saying 32,000 times 10 to the negative third amps times hours. So I added an R there just for a lack of ambiguity. Now you can see that the 10 to the negative third with the 10 to the third here can cancel each other out. And I can just call this 32.000, pretending like I know all those zeros are sig figs, but they probably are not. But I can now call that amps. Whoa, Nelly. Or I can just erase everything because this iPad hates me. I can call that amps. And now the hour, remember, is 60 minutes in an hour, and then there's 60 seconds in a minute. 60 times 60 is 3,600 seconds. So you can see the answer is coulombs. So that's what the actual unit of 32,000 milliamp hours is in. Now it says convert the quantity to its SI base unit. And that's what I've started doing here in B, is I've already started writing it down, but I was doing that so you'd see that the amp is a coulomb per second. And then when you multiply that by the hour, that just gives you coulombs. So now we can take the 32 amps, which is coulombs per second, times the 3,600 seconds, and that's going to give us 32 times 3,600 gives me 115,200 coulombs. Now, obviously, this is probably only 2 sig figs, so this should be, all these should be 9 sig figs. But that's really what, once you charge that portable cell phone charger up, it has the ability to deliver 115,200 coulombs in principle to your phone. And you might say, okay, well, how much does my phone use? Well, you can look up the manufacturer's specifications and it'll tell you, if it's just sitting there, waiting to take calls and stuff like that, it's a much lower usage. If you're playing a bunch of games and stuff, that's going to take more. But the main thing is you can usually get at least 2 charges out of 32,000 milliamp hour. I have one that's 100,000 milliamp hours, and I can usually charge 2, maybe even a third iPhone with that from essentially, like 5, 10 or 20%. I can charge that up to fully charged. But anybody have any questions on that? So that also brings me to another issue, which I'll mention now. So what about which I've mentioned this before, but I want to reiterate, what about the kilowatt hour? That's what, if you're a homeowner or if you're someone who pays your electric bill will come and they'll say you use certain number of kilowatt hours. So are you buying energy? Are you buying current? Or are you buying voltage? What are you buying? Anybody tell from that?
I was gonna say energy.
Yes, it is energy.
Yeah.
Okay, so let me show you 1 kilowatt hour. So this is like another example. It's just not one that I had planned. It's one that I wanted to teach you, sort of as part of the lecture. So I'll just put this here. And what a kilowatt hour is 1,000 watts times 3,600 seconds. You know why the 3,600 is there. And you hopefully know that a kilo means 1,000. That's why the 1,000 is there. But the other thing I'm going to do is I'm going to let you realize that a watt is a joule per second. Hopefully you still remembered that, but you might not have, and that's fine. So that's a joule per second times 3,600 seconds. So you get 3.6 times 10 to the 6th joules. Because you can see the actual seconds cancel out here and there. And 3.6 times 10 to the 3rd is another way of writing 3,600. And then times 1,000 would be 3.6 times 10 to the 6th. So it's 3.6 million joules. And maybe you remember, maybe you don't, a rule of thumb that I like to use and tell my students is a joule is about as much energy as it takes to lift a red delicious, red delicious apple off the ground and lift it to a tabletop. So, a really good firm, basically around the kilogram apple, if you lift that up and lay it on a table, it took just as much energy to lift that one red delicious apple to the tabletop. Therefore, this could lift 3.6 million, 3,600,000 apples could be lifted. So that's not too bad when you start to realize the kilowatt hours are on the order of 20 cents, right? How much would you have to pay a human, for instance, to move 3.6 million apples? Okay. All right. So let's go to our next example, which is example 3. It says a keychain light bulb draws about 200 milliamps, and I'll put a dot there so we recognize that as 3 sig figs. It draws about 200 milliamps when connected to a 1.50 volt AAA battery. What is the resistance of the bulb in this scenario? In other words, I'm saying at this point in time, I've got a 1.5 volt battery running this little keychain flashlight bulb, and it's drawing 200 milliamps at 1.5 volts. So what we want to know is what is the resistance, which means we're going to use Ohm's law. So remember Ohm's law. Y'all should be fairly familiar with this already from lab, but Ohm's law says that V is equal to IR, which can be interpreted a bunch of different ways. One way we interpret it is we say that anything that has a graph of voltage versus current, I on the horizontal axis and V on the vertical axis, and it makes a straight line like that. If it makes a straight line over a large enough area, we call that device an ohmic device. And the reason why is because it has a slope that is a constant, and the slope is in fact R, the resistance. So you can say Ohm's law tells you the voltage if the resistance is R and the current's I, you just multiply I times R, and that gives you the voltage drop across the thing. That's one way of interpreting Ohm's law. Another way of interpreting it is, guess what? Occasionally, you might have something that, for instance, like our light bulb, that had a current I and a voltage V, that varied over time. And for a light bulb, it might have went something like this, in which case you can still interpret the slope as the resistance. But in this case, the slope is a function of temperature. So this would be varying resistances. That might be R1, that'd be R2, and that would be R3. So in that interpretation, Ohm's law is sort of the thing that you multiply the instantaneous current by to get the instantaneous voltage. Okay. So that's sort of the two of the aspects we use for Ohm's law. There's also another version where we use J and J, the current density, which I'm going to show you at the end of this, and E, the electric field, and sigma, which is the conductivity, which is 1 over the rho, which is the resistivity. Okay. So with this one, we're first going to say, what is the resistance of the bulb? Well, using V equals IR, we get V equals IR gives us 1.50 volts is equal to 200 decimal point times 10 to the negative third amps times R, which means R is equal to 200 times 10 to the negative third. Oops, I wrote that upside down. It's 1.50 volts over 200 times 10 to the negative third amps. And this is where hopefully you already know it, but a volt per amp is also going to be defined as an ohm. So if I do 1.5 divided by 200 e to the negative 3, I get 7.500, and that result is ohms. Okay, 1 ohm is defined to be 1 volt per amp, which you can remember a volt is a joule per coulomb and an amp is a coulomb per second. So a joule per coulomb divided by a coulomb per second ends up becoming a joule second per coulomb squared. Not anything helpful, in other words, but I just wanted to show you that's what those things break down to. Okay. So that was part A. Now part B says, assuming the bulb is ohmic, there's that word again, we're going to pretend like no matter what the temperature is, the resistance is still going to be that 7.5 ohms. So it says, assuming the bulb is ohmic, how much current will it draw when a nearly dead 1.20 volt battery is used? So B, we're going to use V equals IR, but this time we're solving for I, which we can see is V over R. So we're going to say that's 1.20 volts divided by 7.500 ohms. So 1.20 divided by 7.5 gives me 0.16. And actually, I can add another non-significant figure on the end of that, and that's amps, which I think you can see is also 160.0 milliamps. Now I'll put the decimal there, but I underline the 0 because really it's only supposed to have 3 sig figs. Everybody get that? Should be pretty straightforward. A lot of this this chapter is really just plug and chug stuff. The next chapter is a little bit more taxing in terms of solving systems of equations, but again, it's the same plug and chug stuff. Now, finally, what is the power dissipated in each case? So this is where I'm going to introduce you to the power, which your book derives. I'm not going to take the time to derive it, but there's various ways of doing so. But power in general is equal to IV. Okay. Now that's really ideal if you've got the current and the voltage, But if you don't have the voltage, for instance, you could use V equals IR and replace that V with IR, in which case you get I squared R. So that's another version of power that you can use. In this case, is really good when you know the current and the resistance. That also happens to be the version you use when you want to calculate how much power is wasted by the power company in taking their huge amounts of current that they're sending from a power plant to various neighborhoods. They run it through the country on those big towers that look like headless, armless people, and they run them at 500,000 or even 1 million or 2 million volts. The reason they do that is it turns out you can use what's called a step-up transformer that takes the voltage from some quantity, say 125 volts, to 125,000 volts. And the way you do it is basically you take the AC, again, we haven't talked about AC, but just bear with me for a second. If you take the AC voltage coming in, and so this is AC in, and you run it through a wire around like a steel, let's imagine a steel Pilgrim's belt buckle. So you remember your Pilgrims in your Thanksgiving plays in grade school, right? If this side had, in fact, N turns, but this side had 1,000 N turns, then 125 volts AC in would give you 125 volts, or excuse me, 125,000. Let's do that. 1,000 volts AC out. Okay. So that's one of the advantages of AC is it's really easy to step up and step down. This belt buckle is literally just plates of steel welded together because that keeps down the eddy currents, and they could put it in a liquid to make it even more efficient. But basically, if you step up the volts from 125 to 125,000, then you've got a really high voltage, and that might not matter to you, but here's why it does matter. When you run the power from a power company, power station, say, to you normally call it a substation, where it breaks down to a lower voltage on the order of 15,000 volts or something like that, and then they send it out to the neighborhoods. The main thing is, the power company is handling X number of houses. Let's say the power company handles 10,000 houses. The way they run electricity to houses is generally you have something called a service entrance, which is where the wires come either off the pole and run into your house, or they come out of the ground and run into your house. And there will be a meter on the side of your house that the power company either can come out and read visually looking at it, or they can come out and read it electronically, or some of them are even connected to the internet, so they can just check at any point in time, or they get it sent to them automatically. But the main thing is the service that a typical house has is 200 amps. So when you buy a house, it's set up to run 200 amps. So 10,000 houses times 200 amps per house gives you basically 2 million amps. Now, according to this equation right here, I squared R, if I use 2 million amps, then I'm going to waste a buttload of power, because that 2 million amps squared becomes 4 times 10 to the 12th, right? And you might think, well, we could also reduce R, but you really can't. I mean, you've got a choice of the cheaper metals. You obviously can't use gold, which has the best, among the best resistivities, in other words, among the lowest resistivities. So you're really just left with copper and aluminum mostly. Copper is a little expensive, so you normally go with aluminum. And then you have an X number of miles that it has to run. So you really have no choice, but basically the number of miles times the resistivity, and then divide it by the cross-sectional area, that's going to be locked in. And not only that, since that resistance is locked in, the voltage drop from the power generating station to the substation is also fixed. So if you can find some way of stepping down the amperage, you would waste less power. Well, guess what? Conservation of energy says that the best you can do is 100% efficiency, which means the current times the voltage is going to stay the same. That's what the energy per second is. So the IV will stay the same. Well, guess what? If you step up the voltage from 125 to 125,000, then the current's going to go from 2 million amps. So let's say 2 times 10 to the 6 amps AC in is going to end up being a factor of 1,000 smaller. So it's going to be, in fact, 2 times 10 to the third amps AC out. So we just reduced the current by a factor of 1,000. And since the power wasted by heat in delivering that power to the substation, it goes like I squared, then that's a factor of 1,000,000 less energy wasted. So that I squared R is exactly the reason that we use really high voltage to go from a power plant to a substation. Now, also, if instead of knowing, not knowing V, let's say we knew V, but we didn't know I, we can also plug in Ohm's law, which says that I is equal to V over R. In that case, you get V squared over R. Now, the reason that I stopped right there when it was I squared R and showed you that is because I didn't want to confuse you with this, because this looks like it might contradict what I just said, because it literally shows the voltage being squared. And the voltage is, of course, higher now than it was, but that's not the voltage they're talking about. The voltage they're talking about is the voltage difference between the power plant and the substation, which if you put the voltage at 200 or 2 million, let's say 125,000 volts at the power station, it's only going to drop a few percent by the time it gets to the substation. That's the voltage that you're going to use. So that's why I said V squared over R isn't necessarily what you're thinking about when you're trying to conserve electricity and bumping the voltage up really high. Any questions on that? All right, well, that's some pretty straightforward stuff. We'll get to this AC stuff and this step up and step down a little later. I just wanted to show you a little peek of where we're going and why some of this is important. Another thing that's important about power is that it turns out when you're actually using power in AC, the formula still works, except you use what's called I root mean square times voltage root mean square. If you're using one of these other forms, you got to watch out. There's some details you got to deal with. So just right now, just know that's the only version that's correct for AC right now. Okay. Your book tells you all the versions. You just have to put some cosines in it and some crazy stuff like that. But if you're dealing with I times V, it's just I the root mean square times V the root mean square, and that gives you the power. That's very important, and it's going to give you one of the most important calculations you can do as a homeowner, adult that might take care of their own yard or might have their own house or something like that. So that's why I'm wanting to pull that out now. I will tell you that when we say a house is wired with 120, they often say it's wired with 120, or they'll say it's wired with 125, something like that. What that is an AC voltage of 120 or 125 volts, and it literally varies between 120, 125. So if you're trying to be conservative and figure out how much current something's going to draw so that you make sure you give the right wire to it, then you should assume it's 125. So that's why we often just use 125, because it's a little safer. But anyways, we'll get to that. Now let's look at the next part. It did say for part C, what is the power in each case? So the power for the case of the 200 milliamps and 1.5 is going to be, let's actually let me kill part of this green. And let me grab part of the green and mark it off this way. And now I'm going to see power for part A. That's going to be the current that we had, which was 200 milliamps. So I'm going to say 2 or just 0.2 times 1.5. And that gives me 0.3 watts. So that's the power wasted or dissipated by the light bulb. I put it in green, so I'm erasing it to redo it now. PA is equal to 0.300 watts. That's how much power is wasted in the step A. If you want to know the power wasted in step B, then that's going to be, we calculated 160 milliamps, so that's 0.16 times 1.2. Yeah, there's 1.2. Okay, so that's 0.1920 watts. And that's with one extra sig fig. Now, the reason I'm doing that is, one, the power wasted is something. It tells you how much batteries, how long the battery's going to last, basically. But it also, when you're dealing with lights, the power output by a light is directly proportional to how bright the light is. So you see that a 0.3 watts is nearly a third bigger, or excuse me, it's nearly 1.5 times bigger than the 1.2 volt power. So yeah, your light bulb would be quite dim. Okay, so that was the last part of that example. Let's go ahead now at 6:33. Let's go ahead and take a break till 6:43, and we'll start back up on my next example. I'm going to stay here in case anybody has any questions, and you're free to ask me them as well. I'm looking at the credits in your textbook in the front cover just to see who the editorial and project managers were. I don't know any of them off the top of my head, so oh well. I could probably turn on my chat. Oh, yeah, I see 2 people have sent chats. Funny. I just saw your comment, Elron. That's me, Cosmo. Chill out, buddy. It's daddy.
Oh, professor.
Y'all better watch out. It's a mad dog on loose.
Professor.
Have to add a diagram to this picture. Got about 5 more minutes for you folks. I'm really disappointed in my resistor there. Not too bad now. That did not make it any better. Fix this. Don't, not too bad. All right, so we got about 2 minutes. All right, let's go ahead and get back started. Does anybody have any questions on this problem that we just did? This chapter 25, like I said, is supposed to be sort of lightning fast, not that difficult. These problems are they're not the hardest, but the problems that I expect you to do are more or less like them, maybe solving for a different variable instead of, for instance, in this case, I solved for R in one case and I in another case. Maybe I'd solve for voltage in another case, or maybe you'd have a little bit of a word problem-esque sort of scenario where you have to, think about two different equations or something like that. But the main thing is these are certainly about the level of the problems that you'll be working. The homework might be a slight bit harder, but the individual test questions won't be much harder. Okay. So that's why I don't feel obligated to do too much more of the, what I'd call god awful or really rough problems. Okay. So no questions on this? Yes. All right, let's flip this over then. So the next example, this was actually sort of like a conceptual example that was done in your book. And it says, consider the figure below. A is the point A or point B at the higher electric potential, and B, if R is 100.0 kiloohms and I is 30.0 milliamps, what is the voltage difference between the points the points A and B? Okay, so first off, I'm asking a question: is point A or point B at the higher electric potential? What is another word for electric potential? Anybody know? Or anybody know what units that's measured in? How about that? Yes, that's right, Elron. Yeah, it should be the volt. Okay. So electric potential, if I stop short and say electric potential, that you should think electric potential is voltage. If you were to go further and say electric potential energy, then it's just potential energy, which is measured in joules. So the other thing would be just called voltage. So voltage is, they often just use the name of the unit for the quantity. So you'd say, VA has a higher volt than VB or has a higher voltage than VB. And that's actually the answer. The reason we know it is conventional current flows from positive to negative, and that means from more positive voltage to less positive voltage. So for part A, we can say, well, for starters, we can take it off of automatic drawing neatness because that sure is an idiot. So for part A, crap, I used the wrong color too. For part A, VA is greater than VB. And I even did that kind of crappy because I made it more like a U. So VA is greater than VB. Current flows from high V to low V. Okay, so that's the main reason we know that. Now for part B, it says if R is 100 kiloohms and I is 30.0 milliamps, what is the voltage? So part B, I did these numbers with these units specifically because I want you to get the idea of how you can use the units and keep them. You don't always have to convert back to amps and ohms. You can keep them sometimes in kilo ohms or mega ohms and stuff like this. So this is going to show you that V is equal to, dang it, V is equal to I times R as Ohm's law. And that literally tells us the voltage change in going across the resistor of resistance R. Since we now know that the voltage A is higher than the voltage B, if we claim the voltage at A was 10 volts, whatever we get for the V here, you subtract that V from 10 volts, and that will be what the voltage is at B. So that's something that we use in circuits, which we're going to see in the next chapter. So really aggravating. Okay. So in this case, it's going to be 30.0 milliamps times 100.0 kilo ohms. Now notice, does anybody recall what a kilo is in terms of a power of 10?
Kilo is 10 to the third,
Exactly. How about a milli?
10 to the negative 3.
Right. So you see in this case, the milli and the kilo cancel out.
Mhm.
So that's what I mean. And, you know, other things like a kilo divided by a milli is actually a mega, stuff like that. So you can use that. But in here, we're just going to multiply the 30 times 100. That gives us 3,000, which is one extra sig fig, of course. And that's 3,000 volts. Okay, so I should technically write that as 3.00 times 10 to the third volts. So 30 milliamps going through 100 kilo ohms. Really, the deal there is the amp times the ohm is a volt. And the 3,000 just indicates that clearly if you want to put something through 100 kilo ohms, you're going to need a buttload of voltage to do it. And that's what you see. So if the voltage right here, say, let me write this out. So if VA equaled 4,500 volts, then VB would equal 4,500 minus 3,000 would be 1,500 volts. So when I draw those bubbles on circuits, I've done it once now, and you'll see it later. But when I draw those bubbles on circuits, that's what I'm going through is I'm trying to assume basically that wires have almost no resistance. So the voltage across from one edge or one end of a wire to the other end should be about the same. If you're going the direction current's going, it's actually going to be a little bit smaller, but it literally could be, you know, a difference of 1 in the third decimal place or a difference of 1 in the second decimal place. That's why we often just treat the wires as if they have no resistance. All right, any questions about example 4? Pretty straightforward, right? All right, let's look at example 5. It says a jumper cable is 2.25 meters long and made of copper wire of diameter 0.92 centimeters. What is its resistance? So this is where I'm going to ask you some questions. And doing that, we're going to basically derive a philosophically correct version of what resistance depends on. And we're going to get the actual right answer. So imagine this is a piece of wire. This little pencil here is a piece of wire. Let's imagine it doesn't have a sharpened point. It's just a cylinder like a straw all the way through. So if you're trying to say, maybe this is big enough to let old people in wheelchairs go through, right? So if you have a bunch of old people in wheelchairs, and you're trying to get them to go through this thing, what's going to take the longest amount of time and therefore be the hardest? Would it be hardest if the straw was really long or if the straw was really short?
It was really long.
Yeah, so resistance is like the difficulty. So we'd say resistance and length are thumbs up, which means they're directly proportional. So we'd say like R is proportional to the length. Now, imagine that instead we have the ability to have this straw be as big or around as, say, a typical hallway to your bathroom. Or you could make it 10 times the cross-sectional area. Which would be the hardest to go through with a bunch of elderly people?
The smaller cross-sectional area.
Right. So that tells you small area means high resistance. So now what we've got is resistance is proportional to L and inversely proportional to A. Now, if we came up with a quantity that measured how bad something was at conducting electricity, in other words, this quantity, let's call it the resistivity. If it's really high, then the resistance is going to be high. That would mean R and this resistivity are thumbs up as well, right? So with that, putting all that stuff together, what we're going to say is that we believe resistance should be given by the resistivity, which is a property of the material. So that's what that rho is, times the length, and inversely proportional to the cross-sectional area. So when we're looking at a pipe, for instance, or a wire, rho is a property of the metal, L is the length, and A is the cross-sectional area. So it turns out that that seems very, reasonable. And in fact, that's exactly the equation we use. So we're going to do that now. We're going to say R is equal to rho L over A. And your book is kind enough to give us various resistivities for metals. And for instance, for copper, it's 1.68 times 10 to the negative 8th. Anybody want to take a guess at what the units would be? Remember, this has to be in ohms. So what do you think the units of rho will be? Yep. Yeah, see, Nora, what you wrote for the resistance, that was right. Now, anybody want to guess what the units of rho would be? You might need to know what's the unit of L. Anybody know that?
Meters, so it would just be meters.
Exactly. So that's exactly what the unit is. It's ohms times meters. So this quantity is 1.68 times 10 to the negative 8 ohm meters times 2.25 meters. And then the area, wires are generally circular. So they said, and it did say diameter, which is a circular parameter. So we're going to take half of that, which is 0.46. So I'm going to say pi times 0.46 times 10 to the negative 2, because it's got to be in meters. And then I got to square that. Okay. So this is what we're going to do. We're going to do 1.68 times e to the negative 8 times 2.55. And then I'm going to divide that. And here's where I'm going to use parentheses because my calculator knows order of operations really well. So I'm going to say divide by left parenthesis 3.14159 times 0.46 e to the negative 2. And now I'm going to square that and close parentheses. And now I get 6.44 times 10 to the negative 4th. 6.444, in fact, times 10 to the negative 4th ohms. So this is literally 0.000644 ohms. So that is really a small amount of resistance. Okay, and that's the answer. Does anybody have any questions on that? And in fact, for these, I should circle that answer. Circle that answer. All right. Anybody have any questions about that? So that's pretty straightforward. Pretty much that's what you always have to do. You can look up, there's a thing called gauge or AWG. That is the parameters that we use to measure wires. So there's a wire, for instance, called number 10, and number 10 wire would be called 10 gauge or 10 AWG or 10 AUG. That wire is in fact pretty thick. And number 8 wire or 8 AUG or 8 gauge wire is even thicker. So it's one of those inverse scales. And in fact, 12 gauge wire is quite small and 16 is even smaller. But you can look up on the internet if you ever need to know that, what that is. Not only will you be able to look up the actual diameter or radiuses in inches or millimeters or whatever, but it'll also allow you to figure out how much current it can carry, because that's an important thing. Where I said earlier about this P equals IRMS times VRMS, that's where that comes in handy. For instance, I was once out front of my yard. I hadn't bought a gas power edger yet, not a weed eater, but the actual edger. I hadn't bought a gas one yet, but I went ahead and bought from a yard sale. I bought an electric one, and the electric one was actually running on like 1800 amps, or excuse me, 1800 watts. And it's, AC, you plug it into an AC outlet. Well, I went and grabbed what looked like a really nice construction level 75-foot extension cord from Tractor Supply, which generally they sell pretty good stuff too. And it's, more for the more serious stuff, because people on farms actually do some serious work. So I grabbed it, didn't think any more of it. I just ignored it. But I started cutting the grass, and then all of a sudden I felt something burning my hand. I looked down and the wire was melting through my hand. It would have been an actually bad scenario. And had I paid closer attention, I would have first used that P formula to calculate what current it carries, and then use that to figure out what size wire I needed, or at least look on the extension cable or the extension cord that I used and see what its maximum amperage was. That's why I said that P equals IRMS VRMS equation is one of the most important. If you can look up what the power is on a given device, all you got to do is take that power, and to be conservative, divide it by 125, and that'll give you the amount of amps. And then you just make sure you only use an extension cord that can carry that many amps. And then some things, like I have a big compressor. With that case, they specifically say do not use an extension cord at all, because it draws a lot of current. And in fact, even if you use a really nice extension cord, it'll flip the breaker, or it'll just turn the thing off. It'll literally turn the compressor off so that it won't work. So that's something to keep in mind. That's why it's super valuable. Let's go to the next part, which actually brings another concept. So it says, if the jumper cable was at 20 degrees Celsius, what will its resistance be at 30 degrees Celsius? So this is one of those weird things where this equation is exactly the same as the equation that we've done before. I think it was in either chapter 17 or 18, where basically what we said was the initial length was equal to, the length was equal to the initial length times 1 plus alpha parentheses t minus t0. So that is the actual same equation for resistance. And it basically just says the change in resistance is proportional to the original resistance and the change in temperature. So your book also, by the way, in that section where we start talking about this resistivity, it actually has a table of resistivities. That's why I knew the copper was 1.68 times 10 to the negative 8. I looked it up some time ago. Plus, that one's kind of stuck in my head. Not only that, I know the temperature coefficient of copper is 0.0068, which, because it's 6.8, I'll remember that. So what I'm telling you is that the change in R is equal to R0 times some constant, which I'm going to call alpha, times the change in temperature, which would be T minus T0. Now, delta R, as always, is final minus initial. That's what delta is supposed to mean. So I could say R minus R0 is equal to R0 times alpha times T minus T0 in parentheses. And that works pretty good. But here's the equation that you'll recognize. When I solve that for R, then I end up getting a common factor of R0 on the right-hand side multiplied by 1 plus alpha T minus T0. And I think you'll remember that looks exactly like the equation we did for length when we did thermal expansion. So what I'm going to do is say that R is equal to R0, which we found R0 was 0.0006444, 0.0006444 ohms times 1 plus, here's where I use my knowledge of the units of alpha. Be thinking, see if y'all can figure out what units alpha has. I think you can probably do that, but alpha is going to be 0.0068. Anybody have any idea what units that is now? Notice it has to be this product here that I'm getting ready to write down has to be added to 1, which has no units. So that might help you figure out what the unit's going to be for alpha. Anyone? Bueller? It's Celsius degrees to the -1 power. And then in this case, we're going to say 30.0 degrees Celsius minus 20.0 degrees Celsius. And when you subtract 2 degrees, we normally take the subtractions answer and put the degree after the C. So that's why the degree came after the C in that unit. So what I'm going to do is say 10 times 0.0068. That gives me 0.068. I'm going to add 1 to it. Now I've got everything inside that square bracket. Now I'm going to multiply that by 0.006444. And this gives me 0.006882. That's 1 extra sig fig ohms. So that's a typical use of how the resistance changes with temperature, but there in fact happens to be another formula. I'm going to go ahead and write that down here now. The other formula is rho is equal to rho at some T0 temperature times 1 plus alpha T minus that same temperature T0. Now, when you go to use these equations, just like I told you when we did thermal expansion for metals and solids and stuff like that, what you want to do is find an alpha for a temperature that ideally would be dead center between the two temperatures that you're doing. So in this case, my ideal scenario would be finding an alpha for 25 degrees Celsius. I only have one here that's specifically listed for 20 degrees Celsius, so I just use that. Depending on how far you go, maybe 10 degrees is too much. I would suspect 10 degrees Celsius is a little much to put on that, but it might not be. It all depends on how the data behaves when you look at it. But ideally, if you're really doing real life problems for engineering, you want to find an alpha that's as close to dead center between them, or you might even want to break it up into 2 or 3 intervals and use the alpha for the middle of each of those intervals and just go up that way. Okay. Any questions on that? All right. So now I'm going to do example 7, which is related to that same problem I was just talking about with the edger that I bought and melted the cord on. So in this case, it says when dealing with AC electricity, I probably need another crossing of my T there. When dealing with AC electricity, the power is given by P IRMS time equals IRMS times VRMS, and in the US, the VRMS is 125. Like I said, it goes between 120, 125. Some people will use 120, some people use 125. But if you're trying to calculate current, you want sort of the worst case scenario. So in this case, it might even be smarter to use 120 because you're solving for I, which means you're going to divide the power by V. The smaller V is, the safer you are. Okay. But anyways, we'll use 125 on this case. Just know, hey, if I'm really trying to find the current, it might be smarter to use 120 as a conservative estimate. So here's how we do this. I am going to say P is equal to IRMS times VRMS. And you don't necessarily know what that is, except you do know what it is from, actually, y'all had a problem like that on your test too, but you know what it is from calculating the average speed of molecules, atoms, electrons for a given temperature. When we actually discuss AC, which is coming soon, I'll tell you exactly how that's done, but it's basically the same thing we learned before. So in this case, what I'm going to say is IRMS is less than or equal to, and I'm doing less than or equal to because I could actually put 120 down there instead of 125, and that would give me a slightly larger I, and therefore give me a little buffer for mistakes. So in this case, solving for I, solving for I have to divide P by VRMS. So I could use 1500 period watts divided by 120 period. Well, let's go ahead and use the figure that I told you. Well, I'll do this and then I'll do the other one. Volts. So 1500 divided by 120, that gives me 12.5 amps. Okay, so I would want to go to a store somewhere if I needed an extension cord and find one that can carry at least 12.5 amps. Now that was the conservative version. In fact, what I was really asked to calculate is P non-conservative, and in this version, I mean non-conservative. Conservative is something you do to protect yourself. Like if you know the wind speed could get up to 130 miles per hour and you need to design a house to deal with that, you might be playing it conservative because some of the gusts are going to be much larger, and you might design the house to withstand 140 mile per hour winds instead of 120. That would be a conservative measure. That's what I mean by saying conservative here. So in this case, I'm going to say 1500 watts, again with a decimal point, divided by 125 decimal place volts. So if I do this, I do 1500 divided by 125, and that gives me 12 exactly amps. And what I wrote up here, because I had already worked out the problem, knew what the result would be. Notice in the red, it says, note 12 gauge or 12 auger wire can carry 10 to 15 amps of current. I just looked that up from the American Electrical Society or something along those lines. And if you ask any licensed electrician, they'll probably know off the top of their head. If they've been doing the same thing over and over again, they might only know a very small range just because that's what they work with every day. So they'll probably know what holds 15 amps. They'll know what holds 30 amps. And they'll probably know what holds 200 amps. But that's just about it. But they can quickly look it up and they know what it means and all that good stuff. Any questions on that? All right, so that's a pretty straightforward deal. You can look up those tables like I told you. Your book does a problem where, for instance, it actually calculates the resistance of some speaker wires. as you know, your stereo would put out a certain amount of current and voltage. And if the speaker wires are super, super long, they might get such a high resistance that the voltage drops so much that you won't get as much power out of your speakers. So that's something you got to mind for. So keep that in mind. There's a neat little problem your book does too. I'm going to do that. Let's imagine for a second that so this is example off the cuff. So imagine we have a piece of wire. Its area is, or let's say its radius, for instance, is let's say its radius is big R. Okay. And its length is little l. Okay. That means the resistance of that wire. Ooh, I should probably have not used big R then. Gee, it's almost like I didn't even see that coming. So let's kill that big R. That's obviously a problem. I'm going to go back and say that that radius is, let's say cursive R. Okay. So the resistance is in fact rho L over A, but A is power squared. So I can say it's rho times L over pi. And here I'm going to do my cursive R squared. Okay. Now, what I want to do is I'm going to stretch the wire until it is twice as long. And then I want to know what will be the new resistance. So that's the big question. What's the new resistance? Well, what we're going to do is we're going to assume, hey, this is a certain amount of mass of copper, and I'm going to be stretching, but I'm not going to be using any kind of supernatural strength or anything. So it's highly unlikely that I'd change the density of copper. So I'm going to say rho copper, which, or whatever material it is, I'm just going to say, assume it's copper, but the rho of copper is going to be a constant. And because of that, we know the mass is constant. So since M is also constant, in other words, we're not going to break off any of the wire. That tells us that V, which remember rho equals M over V, so V is equal to M over rho, will also be a constant. Now V is actually equal to pi R squared times L. So that's still going to be the new volume, but now what's going to happen is I'm going to have some new radius, little r equals question mark, but this new length is going to be exactly what I said it would be, specifically 2L, like that. So now the volume would be pi times little r squared times 2L. Okay. But V equals a constant, which means that pi, which means that pi little r squared times 2L is equal to pi times r squared times L. So you can automatically cancel out this L and this pi, and this L and this pi. And what you're going to get is 2 little r squared is equal to big R squared, which you can interpret to be the square root of 2 times little r quantity squared is equal to big R squared. So you can now say that little r is equal to big R, cursive R, over the square root of 2. Does that make sense to everybody? Have I lost anyone with that one? Everybody follows what I did? All right, so now the resistance will be the row hasn't changed. The length now, of course, is 2L. And now the area is pi times, it's pi times r over the square root of 2 quantity squared. So I can simplify that and say it's going to be rho times L over pi times r squared. But notice when I squared r over the square root of 2, the square root of 2 became 2 when I squared it, and it went to the top. So there was already a 2 up there as well. So now it's 4 times that, which means I've increased the resistance times 4. So the resistance increased by a factor of 4. Ain't that kind of a neat problem? So yeah, if you actually tried to stretch a wire, you already knew it was going to go up in resistance to some extent because you made it longer. But what happened if it got bigger? Well, it can't. It's not going to maintain the same volume. So ultimately, it ends up getting even worse than you might have thought. So, any questions on that? All right. So basically, what we just did is finished all of section 25-4. And the next part is really the last part. So it's the last part in terms of problems you're going to solve. I highly recommend you reading current density and drift speed and electric field inside a wire and superconductivity. All those things are very interesting and have a lot of cool concepts and that sort of stuff. They also have a section on AC, which I'm going to cover in more detail later. But while I'm here, let me go ahead and give you a little rundown on what AC is. So when we talk about AC electricity, that's the stuff that we have in our light receptacles at home. Okay, those little receptacles that we have, for instance, that look like you got a circle and you got another circle like this, and then you have one long slit and then a short slit and then a little eyeball like that, or a little mouth like that. I can never remember on which side the long one is or which one matters. But anyways, if you ever were to have to work on one of these or replace it, I will show you basically what's important about it. This is the receptacle, And it looks like I chose exactly opposite. I'm just looking at my receptacle now, and it does appear that the long one's on the left, not on the right. So let me fix that real quick. I personally, when I'm doing electrical work, I prefer to install it upside down so the little mouth looking thing is on top, which might be the reason that I put the short slit on the wrong side. The reason why I put that hole right here on the top is that hole is the one that's connected to ground. In other words, that's the safe wire. So if your child was running by playing with a little metal sword or something like that, and the light receptacle had the plug just out a little bit, maybe a plug running a lamp, if they were to swipe down with that metal sword and the receptacles were like this, they would hit across these two slots. And those two slots, one of them is quote unquote neutral, a white wire, and the other one's hot, which is black. And that would basically hit them with 120 volts, and that'd be a problem. Whereas if it's upside down, they'd swat down on it or drop something and it'd fall on it. It would just land on the ground wire. And literally, if you followed the little wires from these little mouth holes on all the receptacles, they'd all go to the opposite side of your meter that your meter reader reads. And in there, they would go to one chunk of metal, a big aluminum rod, a big aluminum rail, if you will. And that aluminum rail has a robust wire running out of it, from it, out of the house. And then somewhere nearby, it'll be on a clamp on a rod that's about 1 inch in diameter, and it's copper. I think it's copper coated. And that rod is either 6 or 8 foot long, and they just literally jam it into the ground. So that's literally what the ground is. It just can absorb an infinite amount of charge just about and have no problems. But when you go to connect this, there will be screws. I can never remember which is which, but I'll say that one side is brass and the other side is just sort of a silver. So I'll say either red or blue. Let me fix that. Red or blue is a brass screw. Okay. The other just looks like shiny. Actually, I just realized I don't know how to spell shiny. That's a problem. Like stainless steel. Okay. So the black goes to the brass. And it'll actually say all this on the back of your light receptacle. It'll have all sorts of instructions. There's a little bump thing up here where the screw goes in. This little guy is an actual cutter so that you can actually strip the wire. But the black wire connects to the brass. Okay. And then the white wire goes to the silver screw. And you don't even have to use the screws. If you look in the back, there'll be holes that if you cut it to the right length, you can just jab it in there and you don't even have to do the screws. So that's kind of nice. And then it'll have another screw like up on the top somewhere, say over here. And I'll make it an entirely different color for this one. And in fact, it's often green. And this is where the bare wire or the brown wire will go. So the ground wire, which is either bare or brown, goes to the green screw. So if that's the case, then what you'll see is, yeah, they're always like this. So you're actually connecting them in parallel. So if you had, for instance, another receptacle right here, you'd have blue screws and you'd have red screws. And notice where they're at. They're like in the perfect place. Like if you take the plate off your light receptacle and you loosen the little screw up here and down here, the absolute best looking place to grab it is to put your fingers right there on those blue and red screws, and you will get the crap kicked out of you. Okay, so don't do that. I'm just saying that it's really convenient and it's so easy to do it by mistake. Don't do it, okay? Because that's definitely connecting the circuit for yourself and you're going to get shocked. So when we go to connect them, in fact, we're going to take a wire, connect it to this one, and then we're going to take this wire and connect it to another one, which again would be this side and this side. And then another wire we take, say, and we connect this one to the, oh, that white does not show up good. Let's use gray. We connect that one to that one, and we connect this one to this one, and so on and so forth. So you can see that really what's happening is we have sort of an AC power supply, which we normally write like that with a little sine wave in it. And we go resistor, that's one receptacle or one thing that's plugged into the receptacle. There's the other thing. There's the other thing, dot, 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 because what you're looking at is like, whoa. What you're looking at is like, these could be the gray wires. And these would be the art grace, which I'd call, well, I just say gray because that's what I drew it in there. So I'll leave it at that. And these would be the blue wires. Okay, they're not really blue wires. They're just blue in my drawing. By that, though, you can see that, in fact, they are parallel. And if you look, when we did capacitors, we got exactly the opposite result. But with resistors, 1 over R equivalent in parallel is equal to 1 over R1 plus 1 over R2 plus dot, dot, dot. Mathematically, this means R equivalent in parallel is less than R1, it's less than R2, it's less than R3, dot, dot, dot. That's the nature of this equation. No matter how many resistors you have, the net resistance of them in parallel will be smaller than any one of them. And remember, the voltage is just that VRMS is equal to 125, right? So as the resistance gets smaller and smaller, the current gets higher and higher. And that's why when you have a certain number of light receptacles on one circuit breaker, the resistance has gotten so low that it's drawing, let's say, approaching 30 amps. And if you have a 30 amp circuit breaker, that circuit breaker is going to break at 30 amps and everything's going to turn off. That usually happens with something like a hair dryer, which takes a lot of power. You can find exactly how much current by dividing the power by 120 or 125. A heater, a space heater is another one that takes a lot. if you get enough of those things on one circuit, it will trip the breaker, or if the house is old, it'll have fuses, and fuses are literally just pieces of wire that carries the current through that fuse before it goes to the circuit. And that piece of wire that's in the fuse is designed that when it gets to 30 amps, if it's a 30 amp fuse, it'll melt in two. So don't ever let anybody, talk you into sticking a penny in place of a fuse or whatever. That could really burn your house down. Now, the other rule, by the way, is R equivalent in series is just equal to R1 plus R2 plus R3 plus ... for however many you have. And that means that, basically the more that you put in series, the bigger the resistance is. All right. Now that we've covered all that, I just want to tell you that in general, AC, the voltage as a function of time would be V0, which is called the peak voltage, which is around and double check my math because I haven't done this calculation for 120 in a long time. So it's somewhere between 170 volts and 177 volts. That's what the peak is. And then it's times cosine omega t, like that. That's really what the voltage looks like. Okay. This omega is equal to 2 pi times F, and this F is 60 hertz. Again, that's something that Nikola Tesla gave us, and we still use to this day. Great Britain uses a different electrical system than ours. I think they do use 50 hertz instead of 60, but they also use 240 instead of 120. We use 240, for instance, our stoves and our dryer uses 240 volts. But the way we do it is we don't send out something with a peak that's, 240 times the square root of 2, which is what I got that from. VRMS is actually V0 over the square root of 2. So that's where I got that from. Similarly, IRMS is I0 over the square root of 2. But anyways, what we do is we do something called triphasic, where basically we have, as a function of time, we have one wave that looks like this. And then we delay that by 60 degrees. And then we delay another one by 60 degrees. Like that. And now what that means is you can take, for instance, this trough and line it up, say, with this crest, and you get a net voltage difference of 240, whereas nothing you're doing is actually 240. Everything's, the root mean square is 125 or 120. But because you're doing twice it, going from a trough to a crest, that makes it like 240. So that's called triphasic. And that's the way we do electricity here in the United States. Now, the last thing I want to do, it seems we got about 14 minutes, so that's about perfect. I want to convince you that if you wanted to calculate the drift velocity of the charge carriers in a current carrying wire, what you do is, first off, you'd say, I'm going to invent a quantity, and that quantity is going to be called the current density. And I, the current, is equal to the integral of this current density, which we'll treat like a vector quantity, dotted with dA. So it's the current per unit area. Okay. So obviously that means J would have units of amps per square meter. And in fact, it can vary quite a bit. Oliver Heaviside discovered that a lot of the electricity he was dealing with, basically all the current was out on the outside skin of the wire, not really going through it very much. And in many cases, it was completely outside of the wire. So you can have all sorts of weird current densities, but that's what we're going to try to calculate. So what we're going to say is I, the current, is equal to delta Q over delta T in general. So that's what we're trying to look at. Now, what we have here is a chunk of a conductor like this, and we're going to create electric fields pointing this way. That was supposed to be a red arrow, but it didn't change colors for me. So that's our electric field. And that means that in principle, current should go that way as well. Okay. But in reality, we know what's really happening is little electrons are going this way. And what we're trying to calculate is what is their, I don't know why this keeps coming up here. What is their drift velocity? So in other words, their velocity, I'm going to say is V sub D, and we're trying to work that out. Okay. Well, when I go to do that, what I can do is I can say, okay, well, delta Q is really the number of charges that are going to be moving. So it's the number of charges times the charge per particle. Now we know the particle is actually the electron, so we'll do that. But the number of charges that we mean here is really like how many charges do we get per atom? Like copper, for instance, releases one of its electrons to run around the body of the copper wire, but each atom does that. So if you could count the number of atoms, then you really have the same as the number of charge carriers. So we could say, well, if I knew the number of charge carriers per unit volume, I could take that, which I'll call little n, and multiply it by the volume, which I'll write as this capital V to distinguish it from voltage. This is the number of Q carriers per unit volume. So it's like a density, and this is the volume. And then that gives you the total number of charges. And then, of course, the charge is going to be negative E, because the electrons are the thing moving and their charge is negative E. Now, the number of charges per unit area or per unit volume is kind of difficult, and I'll show you how to do that in a second. But right now, what I'm going to do is, dang it. What I'm going to do right now is I'm going to keep it in terms of N, and then I'm going to realize that the volume that this thing can go through, if it has a time delta T, this distance will be V drift times delta T. That's how far the charge carriers are going to move. And in fact, this right here is the area. So the volume of this would be the area times the drift velocity times delta T, and then all of that times negative E. So ultimately, I get negative E times N times A times V drift times delta T. So now I can say that current, which is approximately delta Q over delta T, is equal to negative E N A VD delta T over delta T. That means those guys are going to cancel out and we're almost there. But if I remember that J is equal to I over A roughly, then you could say J is going to be negative E times N times the drift velocity. And notice the negative sign works perfectly, because if the drift velocity is to the left, multiplying it by a negative means the J is going to point to the right, which is exactly what the current is supposed to do. So that's the actual formula on a microscopic level. And that's something we're going to use. So let's do the following example. So let's say a copper wire with a 0.92 centimeter diameter. In other words, we're looking right back, for instance, at the jumper cables that we were doing earlier, carries, now this part's completely fake, but we're going to say it carries 90.0 amps of current. What I want to know is I want to know the current density. B, the drift velocity. Or drift speed. And C, the thermal speed of E minuses at 20.0 degrees Celsius. Okay, so that's what I'm shooting for. So first off, here's the solution. I know we only got about 5 minutes, so bear with me, please. The solution, first off, for part A, J is going to be I over A. So the A happens to be 90.0 amps. And then the area turns out to be pi times 0.46 times 10 to the negative 2 meters squared. So if I do that, I get 90 divided by parentheses 3.14159 times 0.46 e to the negative 2, and then I'm going to square that, and that gives me a really large current density of 1.354, which actually I only had 2 sig figs on the radius, so I only have 2 sig figs to work with. So 1.354 times 10 to the 6 amps per square meter. So that's one answer. Now part B, they want to know the drift speed. Well, B is a little bit more complicated. So I'm going to flip to here and say B. What we know is that we can think about copper. So for copper, I know, for instance, that copper has a molecular mass, M of copper is equal to 63.5 grams per mole. And a mole, remember, is Avogadro's number, which is 6.02 times 10 to the 23rd per mole. And that could be atoms or electrons or whatever. So I know that. And I also know, for instance, that the density of copper is equal to, notice I used a row there, that's equal to 8.9 times 10 to the third kilograms per cubic meter. So if I consider for a second a mole of copper, then I know that the mole will have a mass of 63.5 grams. And I know also that the density is 8.9 kilograms per cubic meter. So I could, in fact, take the mass, the molecular weight, and I could actually divide that into the number of moles or the number of atoms. Because for copper, as I said, there's 1 electron per atom. So what I can do is I can calculate N as the total number of charges, number of E minuses, which Cu implies 1 E minus per atom. And for a mole, of course, that means the number of atoms is Na, Avogadro's number. And then I'm going to divide that by the volume of a mole. The volume of 1 mole. Well, I don't really know what that is, but I can get that because I know that density is equal to mass over volume. So volume is equal to mass over the density. So what I can do now is I can take Avogadro's number and divide it by the molecular weight for copper, which is being divided by the density for copper. So that would give me 6.02 times 10 to the 23rd E minuses divided by 63.5 times 10 to the negative third kilograms. Remember, 63.5 is grams per mole. So I'm going to take that and divide that by 8.9 kilograms per cubic meter. And you can see now 8.9 times 10 to the third. Oops. Let me do this. So I'm dividing this by 8.9 times 10 to the third kilograms per cubic meter. Okay. So you see the kilograms are definitely going to cancel out with the kilograms, and the cubic meters will come up top. Or excuse me, it'll come, oh, no, it'll come down here. Okay. So when I do this, I'm going to get, 6.02 e to the 23rd. And evidently I got to turn my calculator on. I'm going to divide that by parentheses. Now I'm going to take the 63.5 e to the negative 3 and divide that by 8.9 e to the positive 3, close parentheses, close parentheses. Oh, great. And of course, I got a syntax error. Let's first off, I'm going to go ahead and say 6.02 times 10 to the 23rd E minuses per mole. And then I'm going to say 63.5 e to the -3 divided by 8.9 e to the +3 gives me 7.135 times 10 to the -6. And that should work out to be cubic meters. Okay. So now I can take the 6.02 e to the 23rd and divide it by that answer. And that gives me 8.43, actually 8.44 times 10 to the 28th electrons per cubic meter. So, or cubic meter, excuse me. So clearly we have the right number of electrons per unit volume because the units worked out. Or I should say, at least is consistent with the right number of electrons. So now I can say that J is equal to, in magnitude, E times N times VD. So we can find that, in fact, VD, the drift velocity, should be equal to J over E times N. Well, J we found was 6 point, nope. Where did the J go? I know I calculated it before. Maybe I didn't calculate it before. Oh yeah, I calculated on the previous page, I forgot. 1.354 times 10 to the 6 amps per square meter divided by 1.602 times 10 to the -19th coulombs. And that's per electron. And then I've got N is the number of electrons, so that's 8.44 times 10 to the 28th E minus per cubic meter. So I can now take 1.354 e to the 6 and divide it by parentheses 1.6 e to the -19 times 8.44 e to the 28. And that ultimately gives me meters on top, and the coulombs cancel out with the coulombs per electron. So I get meters per second, and that's 1.00 with one extra sig fig times 10 to the -4th meters per second, which is literally 0.10 millimeters per second. Part C, what we're asked to do there is VRMS is equal to the square root of 2 kT, or excuse me, I think it's 3 kT. Over the mass of the electron, which I think you'll find is quite large. So let's do that real quick. 3 times 1.38 e to the 23rd times 296, or excuse me, 293. And now I'm going to divide that by the mass of the electron, 9.109 times 10 to the -31st. That gives me the square root of 1.33 times 10 to the 56th. Ooh, that's way too high. That's much better. I actually did 10 to the +23 instead of 10 to the -23. So this gives me 1.333 times 10 to the 4th. So times 10 to the 4th. And that's meters squared per second squared. When I take the square root of that, I get the velocity the thermal velocity of electrons should be on the order of 115 meters per second. So way, 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 way faster than what it's actually going. That's it. I'm sorry I kept you 6 minutes late, guys. But that's the last example for chapter 25. We finished chapter 25, and that last calculation is probably the most complicated thing you could do. But the good news is it's the same way. We're just going to take Avogadro's number divided by the molecular weight, which has been divided by the density, and that'll always get us to lowercase n. So you guys are free to go. Let me know if you have any questions. I'll wait for the last person to leave. And that's basically it.
Professor Younger, I had a question about this the homework. So like today we covered chapter 25, and so you cover something about like AC circuit earlier.
Oh
So
yeah, right.
We had a chapter, it was like chapter 30, I believe, was talking about AC circuit. So we don't have to worry about chapter 30, right?
No, I had hoped we'd get there, but we're not going. We're probably not going to be able to get there. So don't.
Okay, I just want to make sure that chapter 30 it was probably not on the final.
Yeah, I doubt I'm getting that far.
Okay.
I'm hoping I can get through 28 and maybe even 29, but that's best case scenario.
All right. So basically this week, like the homework probably till 2026 or 25 maybe.
Yeah, in fact, I'm looking at the homeworks right now. And I've got chapter 24 and 25 sit to 7:30. I'm probably going to push that back to at least 7:31, maybe even August 1.
Okay.
But I don't want it any later than August 1 because the last day of classes is August 2nd, and that's the day I want to have the grades in is that night. So I will change all that. But yeah, that's it. Hopefully we'll get to 28. You can do any of them, whether we covered it or not, and I'll give you
Okay.
extra.
Yeah. So second thing is so when can you actually release or post those like practice final that we can actually use it? Because if I think we're taking on the Monday, so which is probably like only 1 week left actually for us. So
Yeah.
if you can you
yours will be your exam's going to be on the 31st of July, which is a Monday, and I should have it by this Monday. That's normally I give you about a week.
like the coming Monday.
Mhm.
Okay, all right, that sounds good.
All right.
One last thing, it was the last equation you talking about the current density.
Mhm.
When I learned the current density, there's a different formula. I don't know why it's so different. The formula I learned it was a N E. I mean not E. Yeah, it is N times the electrical field and times the Q square and times the main free time and divided by M, which is mass, and then times the A. It was something that differently. I don't know.
Yeah, I've never seen that. You know what class it was in, Bohan?
No, I just got that information online.
Oh, okay.
Yeah.
This is the formula we're using. It's just sort of a statistical calculation. It turns out to be fairly accurate, but yeah, whatever that other one was, ditch it. I don't know what it was. They might be
Okay.
taking.
Yeah, that formula had just had the mass like on the bottom, like on the denominator.
Right.
It's kind of like differently than we had in the books, but I don't know which one.
Okay. Yeah, exactly. Yeah. So this one's a little bit simpler, and hopefully that'll work out for you.
Do we have this kind of question on the exam? Like
the final exam, this could be a question. Yes.
Okay. All right.
And you have a test outstanding for I think chapters 23 and 24. Don't forget to hit those. But other than that, you're good to go.
Yes, I already did those.
Good deal.
Thank you, Professor.
Thank you. Thanks for coming, everybody. And like I said, looks like the test grades were pretty good. So good job. If you didn't do so bad, but you did better than last time, then you're still in a good spot. So just work with me. If you guys need me next week, I might even be able to drive over to the Chesapeake campus. I think Mr. Mitchell's got one more thing he wants to do for you lab wise, but I can come over and help you if y'all have question and answer sessions or whatever at your lab, at least, either Monday or Wednesday of next week. So I can do that. Just let me know.
All right, sounds good. Thank you.
See you, Bohan. Anybody else still
Bye.
here? Looks like Elron's still here. It looks like Nora's still here.
Yeah.
You have a question, Nora?
I had a question, but I don't know if I can ask it if Hellron's in here because it's about the test.
Oh,
I don't think
Elron-
he plans on taking.
No, but I'm actually going to give everybody that didn't take it, I'm going to give them a copy of the test that they can use it to study about. So it's okay. Was it your
Oh, okay.
about the
It was that last question.
Oh, the last one. Gotcha. Yeah, just about everything was
Yeah.
thermodynamics.
What happened?
I said
I'm
just
sorry, I
about
couldn't hear you.
last question was a version of the second law of thermodynamics. So I suspect that's what you're asking about.
Oh, so yeah. Because I selected every answer, and then I was like, I think I might actually be screwing this up completely. And like, what if I'm thinking about a different law or something?
Right. So there was
But
a
I was reading through, and I
version-
think every selection was an answer.
Yeah, there was one in there that was actually the first law of thermodynamics. So, delta U internal equals Q minus W. That was not the second law of thermodynamics.
Oh.
So that was one that a lot of people
Oh.
chose. I'm going to pull it up right now. I can't
Damn.
show it because I don't want to, violation and all that good stuff. But I am going to pull it up so I can look at it to reference it for you. So I'm looking at it right about now.
That was the one. My last selection was the Q minus W.
Yeah, I noticed actually, I looked at specifically yours was the only one where I noticed the name on it. But I looked at it and I saw that you missed one about the heat required to change ice. But if two systems A and B are in thermal equilibrium,
Yeah, with the latent heat.
Yeah, that latent heat one, that's the one you missed. Or that's another one you missed. But one of the answers on the very last question was if two systems A and B are in thermal equilibrium and system B is in thermal equilibrium with a third system C, then A and C are also in thermal equilibrium. That's the zero law of thermodynamics. So that's not the second.
Oh, damn. Oh.
And then delta.
Yeah, but it's true. So I was like, yeah.
Yeah, it is true.
Okay.
And then the other one that you got wrong was delta E internal equals Q minus W. As I said, that was the second law of thermodynamics. I mean, the first law of thermodynamics. For the record, while we're on recording, let me tell you what the first law of thermodynamics in various versions are. One is all reversible engines operating between the same two constant temperatures, T high and T low, have the same efficiency. Any irreversible engine operating between the same two fixed temperatures will have an efficiency less than the efficiency of the reversible engines. So that's one version. There can be no perfect 100% efficient heat engine. That's another version. No device is possible whose sole effect is to transform heat from one system at temperature TL into a second system at temperature TH. In other words, you're going to lose some heat. So that's another version. No device is possible whose sole effect is to transfer a given amount of heat completely into work. The entropy of an isolated system never decreases. It either stays constant in reversible processes or increases in irreversible processes. That's another version. No device is possible whose sole effect is to transfer a given amount of heat completely into work. I evidently put that one twice. I liked it so much. The total entropy of any system plus that of the environment increases as a result of any natural process. That's another version. Natural processes tend to move toward a state of greater disorder. That's another version. And finally, the last version is heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object.
Right.
Okay. So yeah, that was it. Now, what you missed on the latent coefficient of heat, you first got to use the specific heat of ice, which they gave you is like 2090 or something like that. And that's that times the 0.456 kilograms times the
The change in
25
temperature.
degrees is just what's required to bring the ice from -25 to 0.
Oh, I didn't add that to melt it or to boil it, right?
Right. The
Okay,
next thing
that's
you have
yeah.
to do is then take water from 0 degrees Celsius that has 4,182 joules per kilogram Kelvin. You have to do M times C times delta T for another 25 for that. And then you also have to do the heat of vapors or the heat of fusion, which is just the value they gave you. I can't remember what it was, like 1,600 or something times 0.435 and add that. So you end up getting like 225 joules.
Gotcha. I just did M times L, which is the latent heat of ice or something like that. And I was like, all right, yeah. And then just kind of like went for it, but I didn't take the time to actually think it through. And there was another one on there that I wasn't expecting to get correct because I thought I was 2 orders of magnitude off, but it was 40,000 something. That was the one I had kind of memorized from the practice test. So I was like, I know it's one of them. And then I
Yeah.
tried to calculate it on paper. I don't know if you'll be able to see my work or not.
Yeah, I'm looking at it right now. It's a parallel plate capacitor, has a plate
That one.
of
Yeah.
5 centimeters. If the potential energy or potential difference between the plates is 2,000 volts, and with the top plate at the higher potential, what is the electric field? Well, remember the electric field is volts per meter, so you're literally going to take the
Yeah.
2,000 and divide it by 0.05, and that gives you the 40,000.
Exactly.
Yep.
But yeah, a lot of those problems I like where I was able to work them out on paper in like less than 2 or 3 minutes. So
Yeah, that's what I tried to make it. There was supposed to be what I considered 2 difficult problems. And all the others were what I thought would have been really straightforward problems with little or no, I mean, other than a careless mistake, everybody I expected knew how to do it. It's like an ideal gas law.
yeah, the ideal gas law ones, and also you put like 2 examples from like different parts of the chapters like in a row. So that helped a lot too because like I get really like disorganized in my head and I don't know like what's going on tests half the time. So like
Yeah,
when I'm looking at part of the formula sheet, I could stay on that and then move down. So it was helpful.
Good. I'm
But
glad that worked because I actually actively chose not to randomly order the questions specifically because I thought that might help a little bit.
yeah, no, that was wonderful because then I was like, oh great, I can use the same equation. And honestly, tests help me understand content way better. Like
Yeah, it's something that just comes together. That's why testing is actually a good thing pedagogically. So
yeah.
good job on your test. You did really
Thank you.
well. This is still being recorded, so I won't say any more than that, but I'll just tell you good job.
Thank
So,
you.
let me know if you need anything else, and I will see you guys next week.
Sounds good. Have a good one.
Have a good one. Thanks for your help.